Welcome to the deep dive. Today, we're really getting into the nuts and bolts of network security. We're talking firewalls and tunnels.
That's right. These are kind of the digital gatekeepers and secret passages of the internet. They protect your data, your passwords, everything.
Absolutely. And understanding them is, well, it's crucial. Doesn't matter if you're just starting out in InfoSec or you're already deep in the field. This stuff is foundational.
It really is. And we're going to break down not just the basics, but really get into the details of how these technologies work, making it practical.
Our main source for this is Chapter 10 of Computer Security and the Internet, Tools and Jewels, the second edition. It's a great chapter, really lays things out well.
Yep. So our mission today, to give you a solid, deep understanding you can use, for self-study or even in your job.
And hey, to everyone listening on InfoSecTube, welcome. If you want more deep dives like this, definitely hit that like button and subscribe to the channel. Helps us out a lot.
It really does.
Okay, so let's dive in. First up, packet filter firewalls. The basics.
Right. Section 10.1 in the book kicks off with these. Think of a firewall as a security checkpoint, basically. It sits between networks, typically your internal trusted network, like your home or office, and an external untrusted one, like the big, bad internet. Its job is access control.
So it's like the digital equivalent of those heavy fire doors in a building, separating areas.
That's a good analogy. It really embodies that principle of complete mediation, P4, from the security principles. Every single thing trying to cross that boundary has to go through the firewall check.
And isolated compartments too, right? P5, keeping things separate.
Exactly. Figure 10.1 in the book shows it nicely, the firewall right there in the middle. Now, it filters traffic in two directions. Inbound, coming into your network, and outbound, leaving it.
Most people think about blocking stuff coming in, external threats.
And that's critical, definitely. But filtering outbound traffic is just as important. It lets you control what your internal machines are doing.
Like stopping sensitive data getting out, data exfiltration.
Precisely. Or preventing compromised machines inside from phoning home or participating in attacks. It's about enforcing your internal policy, too.
Okay, so how does it actually decide? What's the logic?
It all comes down to rules. A packet filter works based on a rule set you define. Each rule is basically a condition and an action. Condition, action.
If this condition is met, do this action. Simple enough.
Yeah, and the book mentions that many firewalls use a first matching rule approach. They check the packet against the rules top to bottom.
Ah, order matters then.
Hugely. The first rule that matches the packet, that's the action that gets taken. End of story for that packet.
Got it. And what are the typical actions? Allow, obviously.
Right. Allow lets the packet through. Then there's DRP, that's a type 1 deny. The firewall just silently discards the packet, no notification back to the sender.
Just gone.
Poof. Then there's reject, which is a type 2 deny. It also discards the packet, but it sends a message back. Well, for TCP, it usually sends a TCP RST, a reset packet, like slamming the door. For UDP or other protocols, it might send an ICMP destination unreachable message. Basically, it says, nope, not allowed.
Logging. I assume they log this stuff.
Oh, definitely. Most firewalls log their actions allowed, dropped, rejected packets, often using something like syslog, essential for troubleshooting and security audits.
So the condition part of the rule, what packet characteristics does it look at?
The real basics, the bread and butter for packet filters, are usually 5 things from the TCP IP header.
Okay, let's hear them.
Source IP address, where it came from. Source port number, the application port on the sending side. Destination IP address, where it's going. Destination port number, the application port it's trying to reach. And the protocol, TCP, UDP, ICMP, that kind of thing.
The 5-tuple.
Exactly. If it's ICMP, the rule might also look at the ICMP type and code, like, is it a ping request? The book notes you could look at other things, packet size, TCP flags, maybe even payload data like URLs. But that deep payload stuff, that's generally beyond a simple packet filter.
Right, that's getting into more advanced territory.
Yep.
So a basic rule might be like, drop all incoming TCP traffic to port 23, block telnet.
Perfect example, and that would be a stateless rule. Which brings us to a really important distinction the book makes. Stateless versus stateful filters.
Okay, what's the difference there?
A stateless filter looks at each packet completely on its own, no memory. It just checks the headers against the rules, packet by packet.
Okay.
A stateful filter, though, is smarter. It keeps track of active connections. It maintains a state table.
A state table, like it remembers conversations.
Exactly. It knows, for example, if a TCP handshake has completed, which IP addresses and ports are involved, so it can make decisions based on the context of the connection.
Ah, so if I start a web browsing session from inside my network,
Right, an outbound connection. A stateful firewall sees that SYN packet go out, notes it in its state table. When the SYN ACK comes back from the web server,
It knows it's part of that connection I started.
precisely. So it allows the SYN ACK back in even if there's no explicit rule saying allow incoming traffic on port, say, 50,000. It knows it's a legitimate response.
That makes a lot more sense than just blindly checking each packet.
It's much more robust. The book also mentions dynamic packet filters, which often just means stateful firewalls because they dynamically manage state. But it can also mean filters whose rules can change automatically.
Like that FTP example, page 286.
Yeah, exactly. Normal FTP mode is tricky because the server initiates a data connection back to the client on a seemingly random high port. A dynamic stateful firewall understands the FTP control connection, sees the command requesting the data transfer, and dynamically opens a temporary hole to allow that specific incoming data connection, then closes it afterwards.
That is clever. Adapting on the fly.
It is. Now, Table 10.1 in the book has some really good example rules. Want to walk through a couple?
Yeah, definitely. Let's make this concrete.
Okay, so rules 1 and 2 are about blocking spoofed packets pretending to be from an IP address they're not. Important, but we'll cover spoofing later.
Got it. What about something common like email, SMTP?
Right. Rules 3 through 7 deal with SMTP. Rule 3 blocks known spam sources. Rules 4 and 5 manage incoming email to your server. Rule 4 allows TCP connections to your mail server on port 25.
This is a standard SMTP port.
Yep. And Rule 5 allows the replies from your mail server back out. Then Rules 6 and 7 handle outgoing mail. Rule 6 lets your server connect out to other mail servers on port 25, and Rule 7 lets the replies back in.
Okay, that covers email flow. What about web browsing, HTTP?
Rules 8, 9, and A cover that. Rule 8 allows your internal users to connect out to web servers on port 80, standard HTTP.
Right.
Rule 9 is the key stateful one. It allows incoming packets back on high ports, but only if the ACK flag is set in the TCP header.
Meaning it's part of an established connection, not a new attempt from the outside.
Exactly. It won't let someone just initiate a connection to your machine on a high port pretending it's web traffic. And Rule A explicitly blocks any new incoming connection requests on port 80.
So you can browse out, get replies back, but random outsiders can't just connect in to your machine via HTTP. Makes sense.
Very common setup. You initiate, the firewall allows the response. Then we have DNS rules B, C, D, letting your DNS server query others and respond to queries.
Essential for resolving website names.
Absolutely. And then E through H are for ICMP ping. The book kind of defers the security discussion there to the denial of service chapter.
Okay, and then the big one, Rule Z.
Ah, yes, Rule Z, default deny. If a packet doesn't match any of the preceding allow rules, it gets dropped or rejected.
Block everything unless specifically allowed.
That's the safe defaults principle, P2. It's absolutely fundamental for security. You must have a default deny rule at the end.
As opposed to default allow, which sounds risky.
Extremely risky. Default allow means anything you didn't explicitly block gets through. You can't possibly anticipate every bad thing out there. Default deny forces you to think about what should be allowed based on your security policy.
So the firewall rules are basically the technical implementation of the organization's internet security policy.
Perfectly put. That's exactly what they are. Now, the book does caution about just relying on port numbers. Port 80 should be HTTP, but maybe it's not.
Someone could run something else on that port.
Potentially, yeah, on an untrusted host. But in practice, for usability, you often have to allow outbound HTTP, HTTPS, maybe with some blacklisting. And you typically block most inbound connections, perhaps with an allow list for specific trusted sources connecting to specific internal services.
Right, maybe allowing connections just to a few known servers, maybe in a DMZ. Though so we'd get to DMZs later.
We will. The idea is minimizing what's exposed. Firewalls act as these crucial choke points for monitoring and control, but this relies on the idea of a clear perimeter.
Which is getting fuzzier, right?
Yeah.
Wi-Fi, USB drives, people bringing their own devices, BYOD.
Exactly. The classic perimeter model is eroding. Does that mean firewalls are useless now?
I hope not.
Definitely not. They're still vital. For protecting legacy systems, maybe tucked away on a separate network segment. For enforcing policy against remote attackers who don't have insider access. And for defense in depth and network isolation, they're still a core component.
Okay, good. But they do have limitations. The book lists a few.
Yeah, several important ones. The perimeter assumption is one, if it's porous, the firewall's less effective. Malicious insiders are often tricky, as internal traffic might be trusted more. Even trusted users can click on bad links, letting malicious content bypass the firewall if the outbound connection was allowed. Tunneling, which we'll discuss more, can sneak traffic through allowed ports.
Right, hiding one protocol inside another.
Yep. And finally, encryption. If the traffic is encrypted, a basic packet filter can't see inside to check the payload for threats.
Okay, those are significant points. The book also mentions dedicated firewalls versus hybrid appliances. Quick difference.
A dedicated firewall has one job: firewalling. Highly optimized, smaller attack surface, specialist design. A hybrid appliance mixes firewalling with other things: VPN, NAT, maybe intrusion detection, all in one box.
Convenience versus specialization, maybe.
Kind of. Dedicated units often have advantages in security focus, performance for the specific task, and maybe physical isolation.
What about personal firewalls? The software on my laptop.
Hugely important. Host-based firewalls, they run on your actual computer, filtering traffic just for that machine. Absolutely essential on untrusted networks, like public Wi-Fi.
They often pop up asking if you want to allow a new program to accept connections, right? Default denial.
Exactly. Lock by default, ask the user. Then there are distributed firewalls in enterprises where host-based rules are centrally managed. The key takeaway is host defenses complement network defenses. You need both.
Defense in depth again. Makes sense. And IPtables for the Linux folks.
Right. IPtables is the standard Linux command line tool for configuring the kernel's packet filtering rules. It's the way you set up a host-based firewall on Linux. Very powerful.
Okay. And one last thing on packet, filters that tunneling hole using HTTP to carry other stuff. Why don't firewalls just block that?
It's a tough one. The book hints, page 288, that trying to completely block any non-standard use of protocols like HTTP would likely break a lot of legitimate web traffic and services.
Unintended consequences.
Big time.
Right.
Many things tunnel data over HTTP for legitimate reasons. It's a trade-off between security and, well, the internet actually working.
Fascinating balance. Okay, before we move on to proxies, just a reminder to everyone listening, if you're getting value from this deep dive, please do like the video and subscribe to InfoSecTube. It really helps support the channel.
Okay, moving on to section 10.2, proxy firewalls and firewall architectures. So proxies are different from packet filters. They act as intermediaries, sitting between the client and the server.
Like a middleman handling the conversation.
Exactly. The book splits them into two main types: circuit-level and application-level proxies.
And the key things for a proxy are transparency and performance, right? Users shouldn't really notice it's there, and it shouldn't slow things down too much.
Precisely. Transparency can be achieved if the client application knows about the proxy-aware client, or if the network gateway automatically redirects certain traffic to the proxy-aware gateway.
Why did circuit-level proxies first appear? What problem were they solving back in the day?
It was really about balancing protection and access. Early internet gateways needed to let internal users get out to the internet, but organizations were very wary of allowing direct connections in from the untrusted internet.
Right, protecting the internal network was paramount.
So the first kind of clunky solution the book mentions was a manual gateway, a dual-homed host machine with two network cards, one internal, one external, but with routing turned off.
So packets couldn't just flow through.
Nope. Users had to log into this gateway machine and manually transfer files back and forth. Secure maybe, but incredibly inconvenient.
Yeah, that sounds painful. What came next? SOCKS.
Yes, SOCKS, Socket Secure, was a big improvement. Using proxy-aware clients, you had a client library, a proxy server program called SOCT, and the SOCKS protocol between them.
How did that work?
The client application, like your browser, would be SOVKS aware. Instead of connecting directly to, say, a website, it would connect to the SOCT server.
Okay.
The SOCT server would then check if the connection was allowed by policy. If yes, it would make the connection out to the actual website on the client's behalf.
So the external website only ever sees the proxy server's IP address, not the original client's.
Exactly. And once the connection is set up, the circuit-level proxy mostly just copies bytes back and forth between the client and the server. It logs that a connection happened, IPs, ports, data volume, but it generally doesn't look inside the data stream.
So good for controlling outbound access based on policy, but not for inspecting content.
That's the gist. The downside was needing SOTTS-aware client apps, but you could combine them with packet filters for inbound control, add authentication to the proxy. It was a solid step. Oh, and SOCKS supports UDP too, not just TCP. But remember, no inherent encryption here.
Got it. So how do application-level filters differ?
They operate much higher up the stack. Instead of just copying bytes, they use specialized programs that understand the specific application protocol, HTTP, FTP, SMTP, etc.
Like they know what a GET request looks like in HTTP.
Exactly. They can parse the application data itself. This means they can make much smarter decisions and even change the data.
Change it, like filtering out bad stuff.
Yes. An HTTP proxy could strip out malicious scripts from a web page, for instance. This is getting into intrusion prevention territory, which we'll cover later, sometimes called Layer 7 firewalls.
So they can filter based on content, not just addresses and ports. What applications are typically targeted?
The book mentions older ones like Telnet, FTP, but definitely HTTP. And email filtering is a huge area, scanning for spam, malware, phishing links. This deep inspection takes processing power, though.
Needs beefier hardware, probably.
Often, yes. Dedicated processors help.
Okay. The book also defines bastion hosts and dual-homed hosts. Remind us.
A bastion host is a super-hardened server placed in a position where it's exposed to attack, usually handling specific services like web or email for the outside world, locked down tight.
Right.
A dual-homed host is just a machine with two network interfaces connecting to two different networks, like internal and external. If you disable routing on it, it forces traffic to go through applications on the host itself, like a proxy.
Gotcha. Building blocks for bigger architectures. What are some common enterprise firewall setups?
The simplest is just a single screening router doing basic packet filtering. Limited.
Okay.
Better is a screening router plus a bastion host behind it. The router does initial filtering, the bastion handles specific incoming services.
A bit more layered.
Then you get to the DMZ, the demilitarized zone. This is a separate network segment between the external and internal networks.
Like a buffer zone.
Exactly. You put your public-facing servers, web, email, in the DMZ. If one gets compromised, the attacker is still isolated from your internal network. It's defense in depth. And you apply least privilege, P6, within the DMZ to only allow necessary traffic.
And figure 10.4 shows an even more complex setup.
Yeah, that's a classic design. An exterior router facing the internet filters traffic into the DMZ. Inside the DMZ, you have your bastion host. Then an interior router sits between the DMZ and the truly internal network, providing another layer of filtering.
Two routers, a DMZ bastion hosts.
Yes.
Quite robust.
Very robust. The bastion host and the DMZ often act as the proxy gateway for both incoming and outgoing traffic. It's a common and effective architecture. If you're finding these architecture breakdowns useful, do remember to like and subscribe to InfoSecTube. We love digging into these details.
Okay, let's switch gears significantly. Section 10.3, SSH Secure Shell, a cornerstone of secure remote access.
Absolutely. The book starts by hammering home that basic IP is insecure. SSH came along in '95 to fix that, providing an encrypted tunnel. And despite the name, it's not just for shells.
Right. Before SSH, we had things like Telnet or Login, FTP, all sending passwords in the clear.
A nightmare from a security perspective. Anyone sniffing the network could grab your credentials. SSH was designed for confidentiality, integrity, and authentication. Table 10.2 shows the secure replacements.
So it uses TCP for reliability and then builds its own secure tunnel on top.
Yep. The SSH transport layer protocol creates that tunnel, and the beauty is almost any TCP-based application can have its traffic routed securely through that tunnel.
Like getting a remote command prompt, a shell. Figure 10.5 shows the client and server working together.
Exactly. Your local slush client talks to the remote slush daemon. They set up the encrypted tunnel. You type a command locally. It gets encrypted, sent, decrypted by shed, run by the remote shell. Output comes back the same way. The remote app doesn't even know it's being tunneled.
Clever. And SSH is actually 3 protocols layered together.
That's right. First, the transport layer protocol handles server authentication, sets up encryption and integrity protection, negotiates keys. The foundation.
Okay.
Second, the user authentication protocol runs over that secure transport layer to verify the client's identity to the server.
Makes sense.
Third, the connection protocol multiplexes the single secure tunnel into multiple logical channels. So you can have an interactive shell and forward a port and maybe transfer a file all over the same underlying SSH connection.
Very efficient.
Yeah.
How does the user authentication part work? Passwords.
Passwords are one way, yes. Also Kerberos tickets if you're in that kind of environment. But the really common and secure method is client public key authentication.
Ah, using key pairs. How does that flow?
Okay, so you generate a public-private key pair. You put your public key on the server, usually in rasterized keys. When you connect, your client tells the server it wants to use key auth and sends the public key ID. The server checks if it recognizes that public key for your user account. If yes, it sends back a challenge, some random data.
That
Right. Your SSH client uses your private key, which you keep secret, to sign that challenge data, plus the session ID, sends the signature back.
And the server uses the public key it has stored
To verify the signature. If the signature is valid and matches the public key, boom, you're authenticated. No password ever across the network.
Much better. But how does my client know it's talking to the real server and not an imposter? Server authentication.
Good question. That relies on the server's host key. Each SSH server has its own unique public-private key pair. When you connect, the server presents its public host key.
How do I know if I should trust it?
That's the tricky part. The most common method, especially for personal use, is trust on first use, or TOFU. The first time you connect, your client asks, "Hey, I've never seen this key before." Shows fingerprint, trust it.
And if I say yes?
It saves the key, usually in the shown hosts. On future connections, it checked if the server presents the same key. If the key changes, you get a big, scary warning, could be a man-in-the-middle attack.
But 2OQ is weak on the first connection, right? An attacker could intercept that one.
Exactly, that's the weakness. Better practice is to verify that initial key fingerprint through some other trusted channel called the admin. Check a secure website, something out of band.
Are there more robust models, especially for businesses?
Yes, the book describes two. Model 1 is basically the managed known hosts approach, maybe with manual verification first. Model 2 uses SSH certificate authorities, CAs.
Like TLS CAs for websites?
Similar idea, but usually internal to an organization. An internal SSH CA signs the host keys of the company's servers. Clients are configured to trust that CA's public key. When they connect, they verify the host key signature against the trusted CA key. Much more scalable for enterprises.
So centralized trust management makes sense. Why might users get confused between password and public key? Off.
It happens when your private key itself is protected by a passphrase. To use the key, your SSH client needs to unlock it, so it prompts you for a password, basically.
The passphrase for the key, not the account password.
Right, but the prompt might just say, enter password, leading to confusion about what's actually happening underneath.
I see. Okay, SSH port forwarding sounds really useful. Securing insecure apps.
Incredibly useful. You can redirect traffic from an old insecure app through the encrypted SSH tunnel. The book details local port forwarding with the SL flag.
idHL listenport.host.hostport eshto. Looks complicated.
Let's break it down. -L says, listen port on my local machine. Any connection to that local port gets securely forwarded through the SSH tunnel to Shoast.
Okay.
Once it reaches Shoast, the SSH server there decrypts it and connects it to the actual target host on host port. Figure 10.6 shows this well.
So I could make my old HTTP-only app talk to localhost.8080 and SSH forwards that securely to the real web server.
Exactly. The app thinks it's talking locally, but SSH tunnels the traffic securely over the network. Brilliant for legacy stuff.
Very clever. And SCP, secure copy. How does that use SSH?
SCP just piggybacks on SSH. The people command starts in strush connection. Once the secure tunnel is up, the local and remote scrappy processes just transfer the file data through that existing tunnel. Figure 10.7 illustrates it.
So it relies entirely on SSH for the security. What about X11 forwarding? Remote GUIs.
Yeah, SSH can securely tunnel the X11 protocol, letting you run a graphical app on a remote server, but see and interact with its window on your local desktop. Very handy.
Wow, SSH is versatile. What's host-based authentication? Sounds different.
It is. Instead of authenticating the user, it authenticates the client machine itself using its own host key pair. Less common, potentially complex to manage keys, and risky if a trusted client host gets compromised.
Okay, probably stick to user keys or passwords. The book compares file transfer methods too. What are the good secure ones again?
Forget old RCP, auths, SCP is secure, uses SSH. Plain FTP is insecure.
Yeah.
FTPS adds TLS encryption to FTP, so that's secure. And SSH file transfer protocol runs over SSH. It's generally the preferred modern choice. Very robust.
Good summary. And PuTTY is the go-to SSH client for Windows users.
Very popular, yes. Free, open source, implements SSH, and often includes tools for some PPS FTP too.
Now that historical trusted host thing, echhosts.equivae.roasts, why was that so bad?
Oh, it was terrible. It allowed passwordless login from machines listed as trusted. If one trusted machine was compromised, the attacker could hop to all machines that trusted it.
Transitive trust nightmare. Violated isolated compartments and least privilege.
Massively. The Morris worm exploited this back in '88, a classic example of why implicit trust based on just IP or host name is dangerous.
A cautionary tale. And the Port 22 anecdote.
Yeah, just a fun bit of history. Tatu Yalonen, SSH's inventor, asked IANA for port 22 back in '95. It sits right between FTP 21 and Telnet 23, the insecure protocols SSH was designed to replace. Logical choice.
Mouse bit of trivia. Okay, folks, hope you're enjoying this deep dive into SSH. If you are, hit like and subscribe on InfoSecTube for more.
All right, section 10.4, VPNs and encrypted tunnels in general. Back to the basic problem. Standard TCP/IP packets are plain text, visible to anyone on the path.
Easy to snoop on, easy to modify, especially on, say, public Wi-Fi.
Exactly. So you might think just encrypt the whole packet, but as the book points out, that breaks routing.
Why? Oh, because routers need to read the destination IP address in the header. Right? If it's encrypted, they can't route it.
Precisely. So we need smarter approaches, like tunneling. This involves encapsulating the original packet inside another packet.
Putting the original packet, inside a new envelope, outer packet.
Perfect analogy. The outer packet has a new header that routers can read to get it to the tunnel endpoint. The original packet is treated as payload. The payload itself, the original packet, or just its data can then be encrypted.
So tunneling facilitates carrying one data stream inside another, and secure tunnels add encryption and authentication. SSH is one example.
SSH is a great example of a security tunnel. IPsec, which we'll get to, is another major one.
And the cool thing is, this security can be transparent to the applications using the tunnel.
Often, yes. The application just sends data. The tunnel handles the encryption and decryption underneath. This transparency is key to virtual private networks, VPNs.
Okay, so what exactly is a VPN? How's it different from just having your own physically separate network cables?
A physical private network uses physical isolation, dedicated wires, controlled access. A VPN creates a virtual private network over a public network like the internet. It uses encrypted tunnels to make it seem like distant computers or networks are connected on a private, secure link.
Instead of leasing expensive dedicated lines, you use the internet but wrap your traffic in secure tunnels.
That's the core idea. Much more flexible and cost-effective.
What are the main ways VPNs are used? The book shows two cases.
Yeah, Table 10.3 and Figure 10.9 cover them. First is site-to-site VPNs, securely connecting two or more whole networks together, like linking branch offices to headquarters over the internet, makes them act like one big private network.
Okay.
Second is remote access VPNs, allowing individual users, like remote employees, to securely connect into the private corporate network from anywhere on the internet. Their laptop basically becomes part of the office network virtually.
Both very common scenarios. The VPNs aren't magic, right? The book mentions limitations.
Definitely. Because the payload is encrypted, network devices in the middle, like firewalls, lose visibility. They can't easily inspect the tunnel traffic for malware or policy violations.
Makes detecting threats harder at the perimeter.
Yes. And if an attacker is inside your network or tunnels out using an allowed VPN protocol, monitoring that traffic becomes much harder. It also means you could potentially bypass firewall rules by tunneling a blocked protocol inside an allowed one.
So end-host security becomes even more critical when using VPNs.
Absolutely paramount. You lose some network-level visibility, so you need strong defenses on the endpoints themselves.
The book also distinguishes transport mode versus tunnel mode. What's that about?
It's about where the VPN security is applied. In transport mode, Figure 10.9a, the security happens end-to-end, directly between the two communicating hosts. The original IP header is mostly kept, and the VPN protection is applied just to the payload.
Okay, host-to-host security.
Right. In tunnel mode, Figure 10.9b, network gateways usually handle the VPN stuff. The entire original IP packet, header and all, gets wrapped inside a new IP packet with a new header. The new header routes the packet between the VPN gateways, the tunnel endpoints.
And tunnel mode is what you use for site-to-site or remote access VPNs, where one end is a network, not just a single host.
Generally, yes. Tunnel mode encapsulates the original packet, allowing it to traverse the internet and then be unwrapped and delivered to the correct host inside the destination network. Transport mode wouldn't work if the endpoint is a gateway protecting a whole network.
Makes sense. And where do these tunnels fit in the network stack? Figure 10.10.
Good question. TLS and SSH usually operate higher up, sort of around the transport application layers. They secure specific connections or apps. IPsec operates lower down at the network IP layer.
So IPsec can protect everything above it. TCP, UDP, any application.
That's the goal, yes. It provides a foundation of security at the IP layer itself.
Okay, that sets the stage perfectly for digging into IPsec itself. Section 10.5.
All right, IPsec, IP Security Suite. The motivation, as we just said, is providing security directly at the network layer, so higher level protocols inherit it. It's a suite of protocols.
3 core ones.
Yep. IKE Internet Key Exchange for setting up the security parameters and keys. AH authentication header for authentication and integrity, and ESP encapsulating security payload for confidentiality, encryption, and optionally authentication integrity.
Let's start with IKE, key exchange.
Yeah, manually setting up IPsec keys and parameters is a nightmare. IKE automates it. It uses Diffie-Hellman, usually, to let the two ends agree on shared secret keys securely, even over an insecure network.
Clever crypto magic.
It is. IKE negotiates all the parameters, which algorithms to use, like AES for encryption, SHA for hashing, key lengths, key lifetimes. This agreement forms a security association, or SA.
An SA is like a contract for how to secure the traffic for one session.
Pretty much, yeah. And it's usually unidirectional, so you typically need two SAs for a two-way conversation, one inbound, one outbound. Each SA gets a unique ID number called the SPI Security Parameters Index.
SPI. Okay.
Yeah.
And that SPI goes in the IPsec headers.
Exactly. In both AH and EST headers, it tells the receiving end which SA contract to use to process the incoming packet.
Got it. So IKE sets it all up. What do AH and ESP actually do to the packets? Let's take AH first. Figure 10.11.
AH is all about authentication and integrity. It calculates a MACSI, a cryptographic checksum over the packet's payload and the parts of the IP header that shouldn't change in transit, like the source and destination IPs.
Not the whole header, though, because things like TTL change.
Right. Fields that routers modify, like TTL or hop limit, are usually zeroed out before calculating the MACSI, otherwise the check would always fail. AH guarantees the data wasn't tampered with, and it really came from the claimed source IP, at least the source IP in the header it protected.
Does it do encryption?
No. AH is authentication and integrity only. It can also provide anti-replay protection using a sequence number in the AH header. The receiver tracks sequence numbers for that SPI to spot duplicates or old packets.
Okay, so AH proves it's authentic and untampered. What about ESP? Figure 10.12.
ESP, encapsulating security payload, is the one that provides confidentiality through encryption. It encrypts the IP packet's payload.
So it hides the data. Does it also do authentication?
It can, yes.
Yeah.
ESP can also calculate a MAR for authentication and integrity, similar to AH, and it can also do anti-replay with sequence numbers.
So ESP can do both encryption and authentication. Why do we need AH then?
Ah, the million-dollar question. The key difference is what the MAS covers. The EST MASI typically only covers the ESP header and the encrypted payload. It doesn't protect the IP header itself.
So AH protects parts of the IP header, ESP doesn't.
Correct. ESP gives you payload privacy and payload authentication integrity. AH gives you payload and IP header authentication integrity for the immutable parts.
I see the distinction. And both AH and ESP work in transport mode and tunnel mode.
Yes. Just like we discussed for VPNs generally, IPsec transport mode inserts the AH ESP header between the original IP header and the payload, figure 10.13b. Good for host-to-host security.
But not gateway to gateway or remote access to a network.
Right. For those, you need IPsec tunnel mode, figure 10.13c. It wraps the entire original IP packet inside a new IP packet with a new IP header and the AKESP header in between. The outer header gets it between the tunnel endpoints, gateways.
That makes sense. Tunnel mode for VPNs. What about that anti-replay mechanism? Why is it more complex than an SSH?
Because IPsec works at the IP layer, which is inherently unreliable and connectionless. Packets can arrive out of order, get lost, be duplicated. IPsec has to handle sequence numbers and a sliding window explicitly to detect replays.
Whereas SSH runs over TCP.
Which is connection-oriented and already handles sequencing, retransmissions, and ordered delivery. So SSH gets a lot of that anti-replay protection implicitly from TCP itself. IPsec has to build it from scratch.
Gotcha. Now, IPsec is often called heavyweight.
It's just complex, lots of options, lots of protocols, IKE, AH, ESP. Deep integration needed with the OS network stack. Setting it up correctly requires real expertise.
Compared to maybe simpler application-level security.
Yeah. The book mentions different ways it's deployed built into the OS kernel, added as a bump in the stack, or even as dedicated hardware, bump in the wire. It's powerful, but definitely not simple plug and play.
So how does IPsec know which traffic to protect? IPsec policy.
Exactly. Just because an IPsec tunnel exists doesn't mean all traffic uses it. You define policies in a security policy database, SPD.
Okay.
These policies are rules, kind of like firewall rules, based on source-to IP, ports, protocol. They say, if a packet matches these criteria, apply this specific IPsec protection, AH or ESP specific algorithms, using this security association, SPI. It allows very granular control.
And ESP can be configured differently? Like authentication only?
Yep, you can run ESP in authenticate-only mode using null encryption.
Yeah.
You can run it encrypt only, but that's usually a bad idea, no integrity. Or the common way, ESP providing both encryption and authentication. Some setups might even layer AH after ESP, but often ESP alone is used now.
Okay. Lastly, on IPsec NAT, issues in the AH debate.
NAT is a big headache for IPsec, especially AH, because AH protects the IP header addresses, and NAT changes those addresses.
The AH integrity check fails.
Bingo. Packet dropped. ESP has issues too, but there are workarounds like NAT traversal, NAT. This AH incompatibility is a major reason why there's debate about whether AH is still needed.
Since ESP can do authentication of the payload.
Right. Many argue ESP's authentication is good enough for most uses, and avoiding AH simplifies things and improves NAT compatibility. So, lots of modern VPNs just use ESP.
Interesting trade-offs. And WireGuard, a simpler alternative.
Yeah, WireGuard is a newer VPN protocol designed deliberately for simplicity and speed. Uses modern crypto, less configuration complexity, aims to be easier to use and audit than IPsec or OpenVPN. It has a strategy called crypto versioning to handle future algorithm upgrades cleanly, gaining a lot of traction.
Definitely one to watch.
Yeah.
Okay, great stuff on IPsec. If you want to learn more about advanced VPN tech, again, like and subscribe to InfoSecTube.
So we've covered firewalls, SSH, VPNs, IPsec, but understanding how they work really relies on understanding the basics of networking itself. Section 10.6 gives a quick refresher.
Absolutely essential grounding, like knowing grammar before writing an essay. Let's start with IP addresses, the Internet's addressing system.
Right. IP, Internet Protocol, is the heart of TCP/IP. Figure 10.10 shows the stack. An IP address is that logical number assigned to your device on the network. It tells packets where to go. Think of it as the street address.
Different from the MAT address.
Totally different. MAT addresses are physical hardware addresses burned into your network card. They're used for delivery on the local network segment, like Ethernet. IP addresses are logical, used for routing between networks.
Then ARP translates between them on the local network.
Yep. Address Resolution Protocol maps a known IP address to its corresponding MHA address so the final delivery can happen locally. IPv4 uses 32-bit addresses like 192.168.1.1. IPv6 uses 128-bit addresses for a much, much larger address space.
Okay, datagrams and packets, sometimes used interchangeably.
They're related but distinct. At the IP layer, the unit is a datagram IP header plus payload. At the link layer below, like Ethernet, the unit is a packet or frame, which has a maximum size MTU.
MTU, maximum transmission unit.
Right. If an IP datagram is too big for the link's MTU, it gets fragmented into smaller IP fragments.
Huh.
Each fragment gets its own IP header bits to allow reassembly at the final destination, so one datagram might travel as several packets.
Got it. And above IP, at the transport layer, we have TCP and UDP, the two main choices.
Correct. They provide services for applications. UDP, User Datagram Protocol, is connectionless, unreliable, fire and forget. Fast, low overhead, but no guarantees packets arrive or arrive in order. Good for streaming, DNS, some games.
Where speed matters more than perfect delivery.
Exactly. TCP, Transmission Control Protocol, is the opposite. Connection-oriented, reliable, ordered byte stream. It sets up a connection first, the three-way handshake, ensures data arrives correctly, retransmits lost packets, manages flow control. Used for web, HTTP, email, SMTP, SSH. Most things needing reliability.
So how do different applications on the same computer use TCP or UDP without getting mixed up? Ports and sockets.
Precisely. Ports are like apartment numbers on the IP address building, a 16-bit number, 065535. Servers listen on well-known ports, HTTP on 80, HTTPS on 443, SSH on 22. Clients usually pick a random high-numbered ephemeral port for their end of the connection.
And a socket is the combination of IP address and port number.
Yep. IP address plus port is socket. A unique TCP connection is defined by the pair of sockets at both ends. Source IP port, destination IP port.
Okay. And TCP needs that three-way handshake to start.
Yes. Client sends SYN, synchronized. Server replies SYN ACK, synchronized acknowledgement. Client sends ACK acknowledgement. Connection established. Data flows.
And firewalls look for that initial SYN packet with ACK data go to spot new connection attempts.
Often, yes. It's a key indicator. Connections end with FIN finish packets or abruptly with RST reset packets.
Finally, ICMP, the control protocol.
Internet Control Message Protocol runs alongside IP, used for error reporting and diagnostics. Things like destination unreachable, time exceeded, or the echo request reply used by ping.
Ping. Everyone's used ping.
Right. ICMP messages, like type 8 for echo request, type 0 for echo reply, are carried inside IP datagrams. Firewalls often filter ICMP carefully as it can be used for network scanning, ping sweeps, or attacks.
So blocking incoming pings is common.
Quite common, yes. Though you might allow outgoing pings for troubleshooting, it's all about policy.
Ooh. Okay, that networking foundation is crucial. Understanding IP, TCP, UDP, ports. It makes everything else about firewalls and tunnels click into place.
It really does. You can't secure what you don't understand.
Absolutely. And for everyone listening, if this foundational knowledge is helpful, please do support InfoSecTube by liking and subscribing. We want to help you build that strong base. All right, that wraps up our deep dive into firewalls and tunnels, based on Chapter 10 of Computer Security in the Internet, Tools and Jewels. We've covered a ton.
We really have. From packet filters, proxies, SSH, VPN concepts, IPsec details, all the way down to the TCP/IP basics that make it all work.
These are such fundamental tools for protecting networks and data. Understanding them, their strengths, their weaknesses, it's just essential in cybersecurity today.
Couldn't agree more. Whether you're building systems, defending them, or just trying to understand the landscape, this knowledge is key.
So here's a final thought for you, our listeners, to chew on. With remote work and cloud services becoming so dominant, and the idea of a fixed network perimeter dissolving, how do you see the role of the traditional firewall changing in the future? What does perimeter security even mean anymore?
That's a great question, something we'll all be grappling with. And hey, if you found this discussion useful, please hit that like button and subscribe to InfoSecTube for more cybersecurity deep dives.
Definitely. And leave us comments. Let us know what questions you still have or what topics you'd like us to tackle next. We really value your input.
We do indeed.
Thank you so much for joining us today as we explored firewalls and tunnels. We hope this has given you a solid, practical understanding you can build on.
Stay safe out there.
Until next time on The Deep Dive.